Imagine a machine that creates more fuel than it uses. It sounds like magic, or maybe something from a science fiction movie. But on the evening of April 6, 2026, this magic became a reality in India. In a small coastal town called Kalpakkam, just outside of Chennai in Tamil Nadu, a massive piece of machinery woke up. This machine is called the Prototype Fast Breeder Reactor, or PFBR for short. On that Monday evening, scientists announced that the reactor had achieved first criticality. In simple terms, this means the reactor successfully started a self sustaining nuclear chain reaction. It was finally alive. This was not a quick or easy journey. It took over 20 years of hard work, billions of rupees, and the brilliant minds of Indian scientists at the Department of Atomic Energy. With this success, India officially became only the second country in the entire world, right after Russia, to successfully operate a commercial fast breeder reactor of this scale. This is a massive moment of pride, but why is this specific reactor so important? To understand that, we need to look at how normal electricity is made and how this giant machine in Kalpakam completely breaks the rules. Normally, when we want to make electricity, we have to burn something. We burn coal, we burn oil, or we burn natural gas. Even in standard nuclear power plants, we burn a fuel called uranium. As the fuel is used up to create heat, it eventually turns into waste. You always end up with less fuel than you started with. This is a basic rule of energy that we learn in school. But a breeder reactor is entirely different. It is designed to create more fuel than it consumes. While it is producing a massive 500 megawatts of electricity, enough to power hundreds of thousands of homes, it is actually cooking up fresh nuclear fuel inside its core. How does it do this? The secret lies in its clever design. Inside the very center, or the core of the reactor, scientists place a mixture of two elements, plutonium and uranium. This is the primary fuel that burns to create heat. However, scientists wrap this burning core in a thick blanket. This blanket is made entirely of a heavy, non-burning type of uranium known as uranium-238. As the plutonium in the center burns and splits apart, it shoots out tiny, invisible particles called neutrons. These particles fly outwards at incredible speeds and crash into the uranium blanket surrounding the core. When the non-burning uranium in the blanket absorbs these flying particles, a magical transformation happens. It physically changes into a brand new element, plutonium. So by the time the central fuel is finished burning, the outer blanket has been transformed into a fresh batch of high-quality fuel ready to be used again. Now, you might be wondering why it is called a fast breeder reactor. The word fast does not mean the reactor was built quickly or that it produces electricity faster than normal. Instead, it refers to the speed of those tiny invisible particles we just talked about, the neutrons. In a standard nuclear power plant, those particles fly out so fast that they actually miss their targets. So, scientists use ordinary water or heavy water to slow the particles down. When the particles are moving slowly, they are much better at splitting regular uranium to create heat. These slow-moving particles are called thermal neutrons. However, if you want to breed new fuel, slow particles will not work. To force that uranium blanket to transform into plutonium, you have to hit it with particles moving at their absolute top speed. You cannot put any water inside this reactor because water would slow the particles down and ruin the breeding process. The particles inside the Kalpakkam reactor are completely unrestricted. They are fast neutrons. And because the reactor uses fast neutrons to breed fuel, we call it a fast breeder reactor. This brings us to one of the greatest engineering challenges the Indian scientists faced. A nuclear reactor gets incredibly hot. Normally, you pump millions of liters of cold water through the reactor to keep it from melting down. The water absorbs the heat, turns into steam, and spins a turbine to make electricity. But as we just learned, you cannot put water inside a fast breeder reactor. If water gets in, the fast neutrons slow down and the reactor stops working. So, how do you cool down a massively hot nuclear reactor without using water? The Indian engineers used a brilliant but highly dangerous alternative: liquid sodium. Sodium is normally a solid metal, but when it gets very hot, it melts into a silvery flowing liquid. Liquid sodium is absolutely amazing at carrying heat away from the reactor core. More importantly, it does not slow down the fast neutrons. But there is a huge catch. Liquid sodium is highly reactive. If it touches water or even if it touches normal air, it immediately explodes and catches fire. Liquid sodium is highly reactive. If it touches water or even if it touches normal air, it immediately explodes and catches fire. Building a giant machine that pumps 1,750 tons of explosive liquid metal through its pipes without a single leak is incredibly difficult. The entire system has to be sealed perfectly tight. The success of the Kalpakkam reactor proves that Indian engineers have mastered the art of safely handling this extreme liquid metal on a massive scale. To truly understand why the Kalpakkam reactor was built, we have to travel back in time to the 1950s. The father of India's nuclear program, Dr. Homi J. Bhabha, realized that India had a big problem. Our country has very little natural uranium, which is a standard fuel used around the world. If we relied only on uranium, we would always have to buy it from other countries. But Dr. Bhabha noticed something else. While we lack uranium, India holds roughly 25% of the entire world supply of another element called thorium. Where is this thorium? It is mixed into the monosite mineral sands found all along the coastlines of India, especially right here on the beaches of Kerala. We literally have an ocean of future energy sitting on our shores. But thorium has a catch. It cannot start a nuclear fire on its own. It needs to be transformed first. So, Dr. Bhabha created a brilliant three-stage nuclear program. Stage 1 was to build standard reactors that use a small supply of uranium to make electricity, which leaves behind a little bit of plutonium. India has been doing this successfully for decades. Stage 2 is the Kalpakkam fast breeder reactor. This machine takes that leftover plutonium and breeds more of it, multiplying our fuel supply. Once we have bred enough plutonium, we will reach the final step, stage 3. In the future, Indian scientists will take the thorium from the beaches of Kerala and put it into the blanket of these breeder reactors. The fast neutrons will hit the thorium and transform it into a brilliant, endless supply of clean nuclear fuel. The successful start of the Kalpakkam reactor on April 6, 2026 is a crucial bridge to that future. It means India is finally mastering the technology needed to unlock the power of our coastal sands. It promises a future where our country can produce all the electricity it will ever need without pollution, without carbon emissions, and without depending on anyone else in the world.